Okay, I see people are funneling in. Good afternoon, everybody. Thanks for joining our webinar today. My name is Joe Barakat. I'm a senior engineer at Verist Engineering. And this is one of a sequence of webinars that we'll be giving this year. The topic of today's webinar is on CFD modeling for mRNA vaccine production. So a bit of housekeeping. We've muted all participants to ensure that there is no background noise. If you would like to ask a question, please use the chat or raise your hand and we will address your question. This presentation will be recorded and barring any technical difficulties, that recording will be shared with the registrants after the webinar is completed. And if you have any issues at all with the sound or video and so forth, please email Dory at this address or call this phone number with this extension. We'll try to get that taken care of in real time. As I mentioned at the top, this is one of a sequence of webinars that we'll be giving this year. The topic of today's webinars is on computational fluid dynamics modeling, but we provide a number of different webinars on a wide variety of topics, and these topics reflect the expertise of all the consultants at Verist. So one took place in January, and the cadence for these is a monthly basis. Some are paid, some require payment, and some are free. And for more information, you can sign up at this web link, and we'll be updating these on a monthly basis. And we'll have, our plan is to have webinars every month throughout the year. So today's agenda is shown here. I'll start by briefly introducing who we are at Verist, and I'll give some background on myself. And the main meat of the talk will focus on CFD modeling for vaccine production. I'll motivate that at the beginning, why modeling can be used to supplement and support vaccine production, and what are the real benefits of modeling. And then the meat of the talk is going to focus on two main topics. The first is on fluid mixing, both at the benchtop scale and at the production scale. And the second topic is on how we model the kinetics of nanoparticle self-assembly, which is important in mRNA vaccine production in particular. How do we do this, incorporate this into a CFD model, and then ultimately predict nanoparticle size distributions that you would in an experiment? And I'll leave some room at the end for some question and answer. So Verist Engineering is a engineering consulting firm based out of Boston, Massachusetts, although we have remote employees in both Miami and Houston. I'm actually remoting in from Miami. And what we do is essentially provide consulting services to industrial partners all around the world on particularly challenging problems. We have a range of consultants that span a wide range of expertises to provide services in multi-physics simulation. That's my background. We also do work in materials testing and modeling, as well as failure analysis. We're motivated and enthused by bringing the principles of physics, chemistry, and engineering to really, really challenging problems. And that's sort of what distinguishes us as consultants. My background is I'm a chemical engineer by training. I did my PhD at Stanford a number of years ago, did my postdoc at Santa Barbara following my PhD, and then have been with Verist ever since. My background is in microscale flows, so flows on the microfluidic scale, as well as transport phenomena. That is heat and mass transfer, electrochemical transport and reactions, and also in complex fluids, which includes non-Newtonian flows. We're software agnostic at Verist, so we use a number of different softwares depending on the problem we have at hand. I have expertise in both COMSOL multiphysics and ANSYS Fluent, and some of the examples I'll be presenting today use both. And a snapshot of some of the problems I've worked on are shown at the bottom here. This is a suspension jamming problem, a microfluidic device, and a battery pack and a thermal management using forced air convective cooling. As a general practice, we do not publicize any of the work we do with our industrial clients due to trade secrets. So generally all the examples that you'll be seeing today are case studies that we've constructed, not based on any particular client problem, but rather inspired by the assembly of knowledge and experience that we've had modeling mixing processes and self-assembly. So with that preamble, the first question I want to answer is what modeling can bring to vaccine production and why one might want to model a vaccine production process. And to start off, I want to show this cartoon of how the mRNA vaccine for COVID-19 is made. And so this is a long process from conception to administration. At some point in that process, what it really boils down to is mixing of two streams and self-assembly of the components solubilized in those streams to form a product. This is how many vaccines are manufactured, as well as many other drug products. So the image on the right shows the industry standard mixer, which is the confined impinging jet mixer. On the left, you see lipids that are solubilized in an organic stream. These have to mix with an aqueous stream shown on the right that solubilizes the mRNA. Upon mixing, these various components self-assemble to form this very complex structure that's depicted here, which is a lipid nanoparticle. And these lipid nanoparticles then can vary widely in size. These nanoparticles are collected, packaged, stored, and later administered in viral vaccines such as the COVID-19 vaccine. This variation in size can have a pronounced effect on drug delivery efficacy. It turns out that size plays a crucial role in therapeutic efficiency and efficacy. And it also turns out that size can be readily controlled by controlling the mixing of these two streams. This mixing performance is first evaluated at the benchtop scale before later being scaled up all the way to the production scale. And at all stages in this process, from the benchtop all the way to the production scale, computational fluid dynamics can provide a complementary resource, a tool to aid and facilitate in that development. In addition to viral vaccines, it's worth mentioning that lipid nanoparticles, which I mentioned on the previous slide, found many uses in the pharmaceutical industry. On the right here, I'm just showing a snapshot of some of the trade names that are used. These are commercial products that are available for a wide variety of pharmaceutical applications, ranging from cancer therapies, analgesics, antifungals, and photodynamic therapies. So what can CFD models bring to pharmaceutical manufacturing processes? I've highlighted a few of the key takeaways here. So first and foremost, using a well-calibrated CFD model enables a user to predict performance and quality of a process or product. In the case of the mRNA vaccine production process, the main outputs from a CFD simulation include mixing times and prediction of particle size distributions. Both of these are critical to product quality. A second item, which is probably the most important, is developing a physical understanding of a process. So in an experiment, you have control of the inputs and measurement of outputs, but in between, something happens, and that something is usually encased in a black box, immeasurable and unknown to the user. What CFD models bring is a window into that box, and you can get a physical understanding of the processes at play and how these processes compete. So for instance, how does the rate of fluid mixing compete with the kinetics of self-assembly? And which of these limits the production of lipid nanoparticles? For an existing mixer design, you can use a CFD model to calibrate and optimize that mixer design without having to run a sequence of experiments, which may be expensive. You can perform sweeps of material and process parameters, even geometric parameters, to calibrate that mixer just right, so you know exactly what to perform in operation, or what process inputs to use in operation. And finally, even if a mixer design does not exist, prototypes can be developed in silico before committing capital to manufacturing. A lot of our clients come to us with requesting CFD support because they don't want to invest the capital to build a new design. They want to see how that design would work in a theoretical model first before committing the capital. So this can end up saving time and saving costs by using CFD models. At Veris, we have a hierarchical approach to problem solving. You know, our motto is to start simple and to build complexity in sequence. We don't like to start with a fully complex model. We like to develop some understanding before we get there, and typically that's how we'll work. So when we're given a problem, whatever it is, we generally start with an ideation session. You know, and this involves hand drawings, dimensional analysis, scaling arguments, back of the envelope calculations, pen and paper calculations. A lot of times this can be enough. Sometimes clients come to us and ask for a full CFD model, and we'll come back to them and say, hey, you know, pen and paper calculations or semi-analytical models, reduced order models can actually get you 90% of the way there without having to do a fully sophisticated three-dimensional calculation, which can be time and labor intensive. For many problems, of course, that's not the case. Sometimes the physics is so complex that you need a full-scale simulation. And at that stage, we ask, you know, what scale of model is suitable to solve the problem? How will such a model be verified and validated? Is there corroborating experimental data to compare to? What are the important outcomes of a simulation? As a trained simulator and theorist, my default position when I see a simulation is to not believe it until I see corroborating evidence. And finally, as I mentioned at the top, we tend to be software agnostic. We like to choose the right software for the problem at hand, rather than having one hammer and trying to find a nail for that hammer. So at Veris, we're COMSOL certified consultants, but we also use ANSYS Fluent quite regularly for many of the problems that we solve. Each of these softwares has advantages. There is no one-size-fits-all software, and so as a general rule, we try to use the software that's best suited for the CFD problem or any problem that we're posed with. So hopefully that gives some background as to the value of simulation and kind of our hierarchical approach. And in the next two sections of the talk, what I want to focus on is those two topics I stated in the agenda, starting with the physics of fluid mixing and how it may be modeled. So fluid mixing really comes in two variants, laminar mixing and turbulent flow mixing. So in laminar mixing, what we're really looking at is the benchtop scale, the microfluidic scale. At these scales, mixing occurs by the random motion of species, molecular species. This is molecular diffusion. You can extract a characteristic diffusion time. Some of you may be familiar with this, but the characteristic diffusion time typically is the length scale of interest. So say that the effective diameter of a channel. The square of that length scale divided by the diffusivity, which is in units of meters squared per second, gives a time scale. The problem with the benchtop scale is that this diffusion time generally is prohibitively long. If you were to rely on molecular diffusion alone, you would need a very large device in order to achieve good mixing. That is a homogeneous outlet for a heterogeneous mixture at the inlet. What microfluidic mixers do to overcome this is to exploit chaos. These designs shown on the bottom here are chaotic mixers, chaotic mixing designs. And as I'll discuss, chaos can come from a number of different origins. Fluid inertia is a common origin of chaos, as in the serpentine mixer shown here. But in the absence of inertia, as I'll discuss, clever manufacturing and channel geometry can induce stretching and folding of fluid streamlines that induce mixing even in the absence of inertia, as is done in the herringbone mixer shown on the bottom. At larger scales, the production scale, the mechanism of mixing is entirely different. As you scale up a process and the flow goes from the laminar to turbulent flow transition, mixing doesn't occur by molecular diffusion alone. Primarily, it occurs via the breakdown of large eddies into smaller and smaller eddies. You might have heard of the so-called turbulence energy cascade, the successive breakdown of macro scale eddies all the way down to the micro scale. Throughout the turbulence energy cascade, you encounter eddies that are first at the bulk scale of the vessel, what we call the macro mixing length scale. These eddies then break into smaller vortices or mesoscale entities until at the very smallest scale, the scale of the molecules themselves, you have the micro mixing scale. And so each of these scales involve a different mixing time. At the macro and meso scale, the mixing time scales with the turbulent energy density, which is shown here. The main difference being the macro scale really is at the scale of the vessel, whereas the meso scale is really at the scale of the eddies that emerge in the vessel, as is shown in this vortex mixer shown on the bottom here. At the micro mixing scale, two competing physical forces are at play. Momentum diffusion, which is governed by the so-called Kolmogorov time scale, and molecular diffusion, which is the Batchelor time. The difference between these depends on the local Schmidt number, which is the ratio of the kinematic viscosity of the fluid and the scalar diffusivity of the molecular species being mixed. Turbulent mixers are designed such that the process kinetic time, in our case, the self-assembly time for lipid nanoparticles, has to be slower than the longest mixing time, so that mixing itself is not rate limiting. When we approach any CFD model and we're trying to model a mixing process, what that essentially boils down to is coupling momentum conservation, or solving the Navier-Stokes equations, to mass conservation for each molecular species, in which you have an equation that governs their interdiffusion. For anyone versed in computational fluid dynamics or fluid dynamics generally, the Navier-Stokes equations will be quite familiar. And this can come in both a turbulent framework and a laminar framework. And the outputs of this calculation of momentum conservation is the pressure and velocity of the fluid without consideration of the particular species. And depending on if you have a laminar or turbulent flow problem, the solver you would use for solving the Navier-Stokes equations can be quite different. These equations, which give the velocity and pressure, must be coupled to equations that govern conservation of mass for each species. You may have heard of Fick's law of diffusion, which governs the diffusive transport of species under dilute conditions. For mixtures of very concentrated species, in this case, you have water and ethanol mixed at relatively comparable mass fractions, then you must use a more sophisticated set of equations, such as the Maxwell-Stefan equations, with a mixture averaging approximation for the mixture diffusivity. And so the key difference here is that the diffusion coefficient of the species will change depending on the local concentration, which we quantify via the organic or ethanol mass fraction. So the solution of these two equations essentially solves the mixture problem, and the main outputs are mixing times for your process. So in the remainder of this section, I want to go through a number of different case studies, starting with several case studies for laminar flow mixers. The challenge, as I stated, with laminar flow mixing is that diffusion is slow. And so the goal is to achieve rapid, efficient mixing in a microfluidic device without relying solely on diffusion. The solution to that problem is chaos. And so chaotic mixing, i.e. exponential stretching and folding of fluid streamlines, can dramatically enhance mixing beyond the diffusion limit. And I'm going to go over a number of different case studies in 3 prototypical devices that achieve this chaos in a number of ways. All of the simulations I will show here were done in COMSOL multiphysics, and later in this section I'll also show some simulations using ANSYS Fluent. So I want to start with the microfluidic serpentine mixer, which is depicted on the right. If I So what we have here is water being fed in on one channel in blue and ethanol in the other channel. And the eddies are visualized by the streamlines. As these 2 streams feed into this channel, they bombard the walls of these S-shaped baffles. So the serpentine micromixer gets its name from these S-shaped baffles, and there are 5 in a row here. After each baffle, I've taken a cross section and I've plotted the ethanol concentration, where red is 100% ethanol and dark blue is 100% water. You can see as you traverse down the channel, after 5 S-shaped baffles, the mixture goes from being quite heterogeneous to entirely homogeneous. The way this is achieved is through this bombardment, these collision events between the fluid streamlines and these S-shaped baffles as it has to make successive turns. This effect relies on fluid inertia. The Reynolds number, which is the characteristic dimensionless group that compares inertial forces to viscous forces, is much larger than 1 in this scenario. The flow is still laminar, so I want to be clear here. The Reynolds number is not large enough to induce a laminar to turbulent transition, but it is large enough to exploit fluid inertia. And when you do exploit fluid inertia, mixing is dramatically enhanced above the diffusion limit. A similar concept is the ring mixer, right? So again, I'm showing on the bottom here fluid streamlines, water and ethanol, feeding into now these ring-shaped sections, and there are 4 here staggered in sequence. And again, I've taken cross sections at the outlet of each section. This is also a device that relies on fluid inertia, but rather than relying on the collision of streamlines with the walls of these S-shaped baffles, what the ring mixer exploits is what's called Dean flows, or centrifugal secondary flows that occur transverse to the mean flow. So I've taken a cross section here which shows the mean flow colored by ethanol concentration. And the white streamlines that I've highlighted are the secondary flows that are induced by centrifugal forces. These are forces exerted in the plane of the ring, and this Dean number is very closely related to the Reynolds number, right? Recall that the Reynolds number was a ratio of inertial forces to viscous forces. The Dean number is the ratio of centrifugal forces to viscous forces, and so you just take the Reynolds number and multiply the square root of the hydraulic diameter of the channel to the radius of curvature of the ring. That gives a Dean number. When this number is larger than 1, you have these secondary flows in curved channels. The last example I want to bring up for the laminar flow examples is the herringbone mixer. So this is a device that does not require fluid inertia to mix. You can see that the flow rates shown here are much, much smaller than the flow rates I showed in the previous 2 examples. Yet, with not that much channel length, you achieve very good fluid mixing. How is this done? Well, the unique design of the herringbone mixer requires a little bit more manufacturing than the previous 2 geometries. So rather than being a single level device, this is really a 2-level device. There are these grooves that have this alternating herringbone pattern. These grooves are what facilitate mixing by stretching and folding streamlines. This is called the Baker's transform. The Baker's transform really works the way it works is essentially a reference to an analogy of what bread makers use, right? So if anyone's ever worked with dough, the way you work with dough is you stretch and fold the dough until it becomes homogeneous. If you zoom in to the fluid streamlines in this herringbone device, it works in exactly the same way. So each of these grooves essentially cause the fluid streamlines to dip and rise, and that process actually has the effect, if you look at a cross section of this herringbone mixer, of actually stretching and folding streamlines so that the distance between the fluid lamella has shrunk. It's actually converged so that the distance over which those molecules have to hop from one streamline to another is much shorter. And again, this doesn't require fluid inertia, which is remarkable. And that's really emphasized in the next plot. This plot is a plot of the mixing time for all three devices, plotted as a function of the Reynolds number to show the impact of fluid inertia, i.e. flow rate, on the device operation. The way we define the mixing time here is by calculating the standard deviation of the ethanol mass fraction and then dividing that by the mean ethanol mass fraction. That ratio is the coefficient of variation, which is basically a metric of the degree of heterogeneity of your mixture at any given cross-section. We define a mixing time as the time required, or equivalently the residence time required, for the coefficient of variation of the ethanol mass fraction to be cut in half. That defines a mixing time. And on the plot, what you see, if you compare the herringbone, the ring, and the serpentine mixers, is that as you might expect, the serpentine and the ring mixers really only work at high Reynolds numbers. The herringbone mixer operates at a wide range of Reynolds numbers, and in fact shows as good, if not better, performance as the other two mixer designs because it has this added advantage of those staggered alternating herringbone grooves to induce chaos via that Baker's transform. And so it just goes to show that with a little bit of additional manufacturing, you can achieve very good mixing in a microfluidic device, even without relying on inertial eddies. Now, when you scale this process up, you encounter the problem of turbulence, right? So the challenge with scaling up from the benchtop to production scale is that the mechanism of mixing is vastly different. So the goal is to reliably scale up with higher throughput while maintaining the same product quality. On the right here, I'm showing a video of that confined impingement jet mixer that I showed on the first slide. And you can see that this process is inherently unsteady, right? What you have is two fluids impinging upon each other. There is a region where the fluid, there's essentially zero velocity at the impingement zone, but the position of that impingement zone can move from left to right because this is inherently unstable. Turbulent flow mixers are designed to achieve rapid mixing at large flow rates. And we are going to show an example focusing on this confined impinging jet mixer of the different mixing time scales in this device and which ends up being rate limiting. So if you'll recall, there are three important scales that matter, right? The macro scale, the meso scale, and the micro scale. And this image on the right really highlights those scales. So the macro mixing scale is really at the scale of the vessel, right? It's intuitive to think about a stirred tank with impellers that through bulk convection convect the fluid. That's the macro mixing scale. The meso mixing scale is at the scale of the eddies, right? So the vortex shedding that occurs via the turbulence energy cascade is what gives rise to a mixing time at the meso scale. And a good rule of thumb is that the characteristic size for these eddies is related to a characteristic dimension of the device. In this case, the inlet channel diameter. This diameter here really gives you a characteristic size for these eddies. Once those eddies have dissipated, though, and you get down to the scale of the molecules themselves, then the intrinsic viscosity and molecular diffusive processes that occur at those scales, those really govern the micro mixing at those scales. Any of these time scales can be rate limiting. Typically, in most devices, the meso and micro mixing time scales are rate limiting. CFD provides a complementary tool to experimental iteration and design to calculate these time scales and see what really dictates the mixing rate in any given device. So this plot kind of really hammers home in a quantitative way what I discussed on the previous slide. So this is the confined impinging jet mixer, and I've colored in blue the regions of the mixer that are meso mixing limited, And I've colored in red the regions that are micromixing limited. And the way I do this is I calculate two mixing times. The micromixing time really is at the smallest scales, right? So this delta here is a subgrid scale. In a large eddy simulation, it's the filter width. And you can divide this by an effective diffusion coefficient, which is really a combination of the turbulent diffusivity and the molecular diffusivity. The square of this length scale divided by that quantity gives a micromixing time scale. At the mesoscale, what you have is the vortex shedding that occurs as these eddies break down, and that vortex shedding gives rise to bulk gradients in ethanol concentration, and that characteristic variation in ethanol concentration defines the mesomixing scale. What you see from the plot is that the inlet channels where the eddies emerge, in this region of the impingement zone, mesomixing is the dominant rate-limiting mechanism, as well as near the walls. In the bulk of the channel, though, micromixing ends up being the dominant rate-limiting mechanism in the confined impinging jet mixer. We can sum these two time scales to get a total mixing time, and then when we're interested in quantifying device operation over a range of flow rates, we can take the sum of those mixing times and plot versus the Reynolds number in a similar way we did for the laminar mixing device. What you see is that even at very low Reynolds numbers, which for a turbulent flow, 100 is a very low Reynolds number, not low for a laminar flow, but low for a turbulent flow. Even at these low Reynolds numbers, the mixing time is pretty fast, about less than 20 milliseconds, and it gets even smaller as you increase the Reynolds number. And so this just goes to show how tuning the flow and enhancing the turbulence of your process gives rise to much faster mixing times than could ever be achieved in a laminar mixing device. So this summarizes this section of the talk on fluid mixing. The main takeaways are that industrial drug manufacturing relies on mixing of different components between multiple fluid streams. The key challenge is scaling up from the benchtop scale to the production scale. At the benchtop scale, you're limited by diffusion, and there's a number of ways you can get around that using inertia or via the Baker's transform. At the turbulent scale, the challenge is that different physical mechanisms can actually limit your mixing, right? And these are very device dependent, right? We showed one example, the confined impinging jet mixer, because that's the industry standard for mRNA vaccine production. We've also simulated other mixer types such as T mixers and multi-inlet vortex mixers, and so on and so on. And these devices all bring interesting nuances to the problem. So for instance, in the confined impinging jet mixer, what we showed was that most of the device is micromixing limited with some mesomixing at the walls. In the T mixer, micromixing actually is dominant and there's very, very little mesomixing at all. In the multi-inlet vortex mixer, you have a combination of both meso and microscale mixing. These other devices also have the added advantage compared to the confined impinging jet mixer of not requiring matched momenta of the two inlet streams, right? So if you recall that stagnation zone is stable or quasi-stable only by virtue of the matched momenta of the inlet streams in the confined impinging jet mixer. CFD simulations provide a complementary tool for process development in this case. It could predict target mixing times, help achieve mixing that's commensurate with your process kinetics, and optimize a mixer to know what process inputs are most desired to achieve target mixing times and outcomes. So I want to end, this is the last section of the talk, and I want to bring in now the kinetics of self-assembly and how that may be incorporated into a CFD model. So what I'm showing here, similar to the first slide, is a prototypical mRNA vaccine formulation, right? So again, you have mixing of two inlet streams, an organic stream and a water-soluble stream, or sorry, an aqueous stream. The aqueous stream solubilizes the mRNA, whereas the organic stream, such as ethanol, solubilizes the lipids. as they mix and self-assemble spontaneously, they form these lipid nanoparticles. And this is a very complicated process, right? There's many different components here, and I'm only giving a very simplified snapshot. There's actually many, many components in any given formulation, and each of these components has a job. So for instance, the ionizable lipids are necessary to neutralize the charge of the mRNA. They effectively encapsulate the mRNA, whereas the neutral lipids and pegylated lipids provide a core outer shell. The pegylated lipids are necessary to increase biocompatibility of these nanoparticles and also controls their size. And so this is very complicated, and I cannot stress this enough. The key thing with modeling is to try and take a complicated process such as this and recognize how can I simplify this to extract the key physics and the key outcomes that I want without compromising the essence of the self-assembly process. Why would we want to do this? Why does this matter? So at the beginning of this talk, I mentioned that delivery efficacy is really sensitive to lipid nanoparticle size. This plot from this paper that I extracted from the literature really emphasizes that. So this is a case where the in vitro activity of siRNA lipid nanoparticles was quantified via gene expression for different nanoparticles with different amounts of those pegylated lipids, right? So as you increase the pegylation content, the size of the lipid nanoparticles drops from 67 nanometers to 37 nanometers. What you see as you decrease the size of the lipid nanoparticles is that the activity of those lipid nanoparticles increases. In other words, smaller lipid nanoparticles more readily penetrate tissue to deliver mRNA or siRNA in this case. And this is a general heuristic, right? Smaller sizes can more efficiently penetrate. And this is important because mRNA vaccine delivery typically exhibits low yield. It's really important to deluge a patient with a large dose in order to extract the therapeutic outcome that you want. And as I mentioned at the beginning of this talk, those size populations can be controlled by controlling the mixing time. In general, longer mixing times give rise to larger aggregates and more heterogeneous lipid nanoparticles, while shorter mixing times give rise to smaller particles and lower yield. So the challenge is that precise tuning can oftentimes be experimentally costly through iterative experimentation. And if you have a given process for a given design and you want to change that design, the cost increases and the time and labor increases. That's really what motivates simulation-guided design. CFD models, if properly calibrated, can provide a very useful tool to see how process inputs impact the size populations of lipid nanoparticles. Now, to do that is challenging, right? So what I'm going to show today is a very simplified model for lipid nanoparticle self-assembly. So if you recall, a traditional vaccine formulation has many, many components. What I'm going to show you today is what happens when you break that down to even one component, that of vesicle self-assembly, the self-assembly of monomeric lipids into a bilayer aggregate structure called a vesicle. This process is well characterized. It's been studied for decades and decades. What basically happens is that monomeric lipids first nucleate these small bilayer sheets, which can be approximated as discs, which are pretty small typically upon nucleation. Those bilayer discs then grow via binary collision events or aggregation. Those binary aggregation events cause the sheets to grow and grow and grow to larger sizes until eventually they grow large enough that they will close. The closure occurs because as they grow, there's a competition between the bending energy for curving the sheet and the edge energy, the penalty that's paid for there being these free lipids at the edge. Beyond a critical size, they'll want to close, and that process is stochastic. There's some thermal fluctuations in here, and that stochasticity gives rise to a size population. Each of these processes can be modeled using the population balance equation. So this is an equation that finds many uses in the pharmaceutical industry, ranging from bubble column reactors to polymerization and crystallization and many other technologies and applications. I'm going to be using it here to model this process, right? So this is basically a transport equation for the aggregate distribution function that varies in space and time and also varies by the number of lipids per aggregate. So each of these number of lipids per aggregate can be binned, and that dictates a binning of the aggregate size. Each of these steps in this process corresponds to a term at the right-hand side of this population balance equation. Right, so the fast nucleation occurs at a typical nucleus size. Aggregation through these integral terms in the population balance equation gives rise to birth and deaths of new aggregates until finally they close, and that closure prevents them from growing any further. To simplify the problem even further, we're going to focus only on the aggregation step. We're going to assume that aggregation is the rate limiting step, as it is typically the slow step in lipid nanoparticle self-assembly. And that aggregation of bilayer sheets into larger sheets will be quantified via these integral terms in our population balance model. So we implement this model using ANSYS Fluent for the serpentine micromixer that I showed on a previous slide. We simulated vesicle self-assembly at flow rates, or at Reynolds numbers rather, ranging from 20 to 100. So we are exploiting inertia here. So the lipids are distributed in the ethanol. They rapidly precipitate out nuclei or bilayer disks that subsequently aggregate as they progress down the channel. We assume that aggregation is the rate limiting step, so we neglect the fast processes of nucleation and closure, but rather only focus on what aggregation does to the size population of these bilayer sheets. And we're going to study this as a function of two process inputs: the total flow rate, which is the sum of the flow rates of these two streams, and the flow rate ratio, which is the ratio of the flow rates of these two streams. And these are the typical process inputs that are used to control mixing at the benchtop scale. So here's a sample of what our model can predict, right? So lipids are fed in the ethanol stream, and I've colored the ethanol mass fraction on the top here. And I've sampled at different cross sections what the particle size distribution looks like at various points down the channel. So at the inlet, you see you have a monomodal, sharply peaked distribution at the inlet. And that makes sense. So upon mixing, lipids rapidly precipitate out to form nuclei of a pretty narrow size range. As time progresses and these bilayer disks collide through these binary collision events, they'll grow and the size population broadens to larger and larger particle diameters. And so the number fraction of any given bin of size goes down, right? But the total mass is conserved here, and so the distribution effectively broadens. You get a larger number, a fewer number of larger aggregates, but those aggregates are distributed. And so we can quantify what happens when we change the total flow rate and the flow rate ratio. So on the right here, I'm showing two plots, right? So on the top right, I'm showing different total flow rates, which are the sum of the two flow rates of the water and ethanol streams, on the size distribution. So the blue curve is the lowest flow rate, and the green curve is the highest flow rate. On the bottom, I've calculated the average diameter, right, which is near the peak of these distributions, and I've also quantified the standard deviation, which is really the spread or the polydispersity of these size populations. What you can see from these plots is that as I increase the total flow rate, that increase in total flow rate tends to shift the distribution from right to left. In other words, to smaller particles, right? And this is most easily seen in the bottom plot, where the average diameter of the nanoparticles decreases as you increase the total flow rate. Why does this happen? One might intuitively think that if you increase the total flow rate, i.e. exploit more fluid inertia, you get better mixing, and so therefore you should get larger particles. But as it turns out, when you increase the total flow rate, you're also decreasing the residence time for lipid aggregation. You're essentially not allowing any opportunity for these bilayer disks that have nucleated to find each other, collide, and aggregate into larger aggregates. That ends up dominating. And that's what actually that's what actually causes the smaller aggregates at the outlet for the higher flow rates. Now, if I instead keep the total flow rate fixed, but only change the ratio of water to ethanol, that's the flow rate ratio, we can also quantify how that impacts the size distribution. So the blue curve here is the smallest flow rate ratio, a flow rate ratio of 1, right? So this means equal amounts of water and ethanol in your system that are being pumped into your system per unit of time. A flow rate ratio of 9 implies that you have much, much more water compared to ethanol in your system that's being pumped in per unit time. What you see, and this is shown in the average diameter plot on the bottom here, which has the same meaning as in the previous slide, what you see is that as you increase the flow rate ratio, the size distribution shifts to the left and the average size drops. Why does this occur? The main reason is that you've essentially diluted the system here. You've actually diluted the overall concentration of lipids and therefore aggregates. Binary aggregation is a concentration squared event. In other words, the rate of aggregation scales with the square of concentration of those aggregates. So if you've diluted down the entire system, you're essentially slowing the rate of aggregation. And that effect results in smaller aggregates at the outlet, or smaller lipid nanoparticles. We can take these two results of the total flow rate and the flow rate ratio and compare them to experimental data, right? So we try to be cognizant of what's in the scientific literature and what our experimental partners provide us. This is an example from 2017 with a herringbone mixer, which I discussed previously. What they did was measure the size populations at different flow rates and different flow rate ratios. And what you can see are qualitatively the same trends that we see in our CFD simulation for a serpentine mixer, right? So as you increase the total flow rate or increase the flow rate ratio, the average diameter drops and the population distribution shifts to the left. And so this is somewhat reassuring that even though we have a very simple model, right, we've only considered aggregation amongst bilayer fragments, even that model qualitatively reproduces the same physics that is seen in experiment. And so this summarizes the second section of my talk, right? Lipid nanoparticles have many uses in the pharmaceutical industry, including mRNA vaccines. And what's really critical is lipid nanoparticle size. Right? It's of interest to predict and tune a process to achieve a target size distribution. That can be achieved using the population balance equation. We showed a very simple model where we only coupled convection and aggregation being the rate limiting step of self-assembly. And our ANSYS Fluent model predicts that increasing the total flow rate or flow rate ratio results in smaller nanoparticles with a much tighter size distribution. That result is supported by experimental evidence in the literature. And so when you're scaling up, so we showed an example from the benchtop, and to scale that up to the production scale, it's very important to have a good handle on the kinetics of your process. Knowing the process kinetic time is key in CFD simulations to scale up a process from the benchtop scale, where laminar flow and you have deterministic streamlines are at play, to the turbulent flow scale where you have stochastic streamlines, fluctuations, much more chaotic flow patterns. To have confidence in those models means you have to have confidence in the kinetics of your process. And so hopefully I've given you some insight into how CFD simulations can help with development. And so with that, thank you for your attention. This is the last slide in the deck. I'd like to devote the rest of this webinar to take any questions that you may have. Thanks for listening.